Hello, chemists. This is Miss Placino, and you are watching lesson 6.3 on molar mass and percent composition. Today's lesson is going to discuss how to calculate percent composition. Some goals for today's lesson. You should be able to calculate molar mass and formula mass. You should be able to explain the differences between molar mass and formula mass. You should be able to calculate the percent composition by mass of the elements in a compound. You're going to be able to explain what a hydrate substance is and calculate the percent hydration by mass of a hydrate. I know this sounds like a lot. The big ones for today are calculating molar mass and formula mass and calculating percent composition by mass. These last, I guess the third and the last one are pretty closely related. You're definitely going to want a calculator and a reference table for today's lesson. So make sure you have those. And if you're ready to go, let's get started. We're going to start by discussing formula mass, which is also called atomic mass. There's two different ways of expressing the same exact idea. To calculate this value, all you do is take the sum of the average atomic masses of all of the atoms in the compound, and this is measured in U or in AMU. Both will do. So let's say that we're looking at a molecule of water, H2O. I'll tell you the one water molecule has a mass of about 18.0 U. In order to find that information, I need to find the mass of hydrogen atoms. I have two of them present in the compound. And I need to know the mass of an oxygen atom. Kind of tough to see on the red, but I think you can. And if I add those together, I'll get the mass of one H2O molecule. So in order to get the average atomic masses of hydrogen and oxygen, all I need to do is look up those elements on the periodic table. Hydrogen has a mass of 1 AMU, and oxygen has a mass of 16 AMUs. So I've got two hydrogen atoms, so 2 times 1 plus 1 times 16 gives me 18 U's. So that is the mass of one water molecule. Let's try out some practice problems. All right, so we're into the practice problems, and I want to go through FEBR2 together. So in order to find the formula mass or the atomic mass, again, remember those are just two different ways of saying the same thing, I need to use the periodic table to find the average atomic mass of, in this case, iron and bromine. So let's take a quick look and do that now. Iron, number 26 on the periodic table. It's asking us to round these to the hundreds place. So an iron atom has a mass of 55.85 U. And if I just kind of go across that period, I'll run into bromine. I know two bromine atoms are present, and I've got an atomic mass of 79.90 U. So I would just take 2 times 79.90 and add that to the molar mass of iron, 55.85, rounded to the nearest hundredth U. So if I grind through that calculation, I would come up with about 215.85 U. And that's it. That's all there is to it. It's really just taking the subscript times the atomic mass for each element present and then adding them together. Pause the video, try out P4O10 on your own. All right, let's check and see how you did. P4O10, I've got 4 phosphorus atoms, 10 oxygen atoms. And to the nearest tenth of a atomic mass unit, I come up with 283.89 U. That's it. Again, 4 times phosphorus plus 10 times oxygen, and I should come up with the formula mass or atomic mass for that molecule. All right, let's get back to the notes. As you might imagine, it's pretty rare for a chemist or any scientist for that matter to be working with one single molecule of any substance. We're generally going to have hundreds of thousands of millions of molecules together. Also, in a lab, we don't really have any scales that measure to unified atomic mass units. Instead, we see grams. So molar mass is a value that's going to be much more useful to us as chemists than atomic mass. Molar mass is the mass of 1 mole of a pure substance, so 1 mole of a compound or element, and we're going to measure it in terms of grams per mole. Now, I know you know the unit grams before, but you might be new to the unit mole. We're going to spend more time in the next lesson really digging into the mole, but the mole is a word that is going to kind of have a number attached to it. So like when I say dozen, you know that means 12. Well, when you say mole, a chemist knows that you mean 6.02 times 10 to the 23rd. So this is a gigantic number, really difficult to kind of wrap your head around just how huge that number is, but we're going to use it in chemistry a lot. So if I want to know the mass of 1 mole of water molecules, the rookie mistake that most new chemists make is somehow trying to use that value. They try to make this math much more complicated than it actually is. But if I'm to take 6.02 times 10 to the 23rd water molecules, it has a mass of 18.0 grams. Well, that number should look really familiar to you from the previous slide. The mass of 1 water molecule was 18.0 U. This is 18.0 grams. So the math behind finding the number itself is exactly the same. It's really just a change in unit. So I would take the mass of 2 moles of hydrogen, added the mass of 2 moles of oxygen to find the mass of 1 mole of water. Same calculation, different units. Let's go back to the notes for just a moment. If you want to find the molar mass of iron 2 bromide and tetraphosphorus tectoxide, do not pick up a calculator. You already did the heavy lifting. The numerical value for formula mass and molar mass is exactly the same. The only difference is the units. So if I had a mole of iron 2 bromide molecules, they'd have a mass of 215.85 grams per mole. No calculator needed for this one. You know it's formula mass. It's really just a change in units. Same deal for a covalently bonded molecule. The number stays the same. The units are what change. Again, molar mass is going to prove to be much more useful for us, especially as we kind of get moving in this unit and really throughout our study of chemistry than formula mass, but it's the same calculation. All right, let's get back to the notes. Hopefully you feel pretty confident calculating the molar mass of a compound. The next calculation I want to tackle is percent composition by mass. So it might be useful to know what percent of a molecule is made up of a specific element. In order to do that, we can use this formula, kind of just a general formula. We can find the total mass that's contributed by an element and then divide that by the molar mass of a compound. So let's say we're looking at water, just because we've done a couple examples with this molecule already. If I want to know the percent composition by mass of hydrogen in a water molecule, I need to know the molecule's molar mass. We know that already. We calculated that. H2O has a molar mass of 18.0 grams per mole. I know that each of the hydrogens have a molar mass of 1 gram per mole. And there are 2 of those, so we'll multiply by 2. So I know the total mass contributed by the element hydrogen is 2 grams per mole. I know the molar mass of the compound is 18 grams per mole, so I just divide 2 by 18, multiply by 100. So the percent composition by mass of hydrogen in water is 11%. Pretty safe to assume the remaining 89% of the molecule is made up of oxygen. You can do the math. 16 divided by 18 times 100 does give you pretty close to 89%. Let's try out a practice problem. Let's see if we can figure out the percent composition by mass of barium and bromine in the compound BaBr2. The first order of business is really going through and finding the molar mass of barium bromide. Pause the video, take a second, look up barium and bromine, and figure out that compound's molar mass. To the nearest whole number, I get a molar mass of 297 grams per mole. All right. So if I want to look at barium, I know that barium has a molar mass of 137.3 grams per mole. I know the molar mass of this compound is 297 grams per mole. And since it's a percentage, I'll multiply by 100. And now I'm set up to figure out percent composition of barium in this compound. The grams per mole will just cancel each other out. And to the nearest whole number, I get a percent mass of approximately 46%. Again, since this is just a binary ionic compound, we can assume that the remaining 54% is made up of bromine. Let's prove it mathematically. I know I've got 2 moles of bromine present per mole of barium bromide. And the bromine has a molar mass of about 79.9 grams per mole. If you round it up to 80, not a big deal. I'm going to divide by 297 grams per mole, since that's the molar mass of barium bromide. Multiply by 100. And if you grind through the calculation, you'll definitely prove that the remaining 54% is in fact made up of bromine. That's it. So make sure that you're using the periodic table. Be really careful about calculating molar mass. It's easy to make careless mistakes. And you want to make sure, like in this case, I've got 2 bromines. Remember to multiply by 2. All right, let's wrap up the notes. The last little bit that we're going to finish up today revolves around percent hydration and hydrates. When you hear the word hydration or hydrate, what small molecule comes to mind? Not hydrogen, that's more of just an element. Hopefully you're thinking water, H2O. And it turns out that hydrates, which can exist as these really pretty crystal structures, are just compounds containing water molecules in their crystal structure. So you can get these different chemical compounds that are able to absorb water from their atmosphere, or just kind of hold on to water and incorporate it into the crystalline structure itself. So if you were able to take this compound, copper 2 sulfate pentahydrate, and like zoom in close enough to see the individual atoms and molecules that make it up, you'd see something that looks like this. You have your copper 2 plus ion and your sulfate 2 minus ion. And then we also have these water molecules that are attracted to the positively charged cation. You can see the oxygens are kind of all lined up pointing at it, and to the sulfate ion. And we have our kind of positively charged hydrogens lined up with one of the oxygens on the sulfate polyatomic ion. So we've got these water molecules just incorporated into the crystalline structure. And we can figure out the percent hydration by mass. Basically, we would take the mass of water, divide it by the molar mass of the hydrate, and multiply by 100. We know the molar mass of water is 18 grams per mole. But in something like copper 2 sulfate pentahydrate, the penta is telling us that there are 5 water molecules present. So I would need to multiply that by 5 to find the total mass of all the water present. When I go to find the molar mass of the hydrate, I've got to find copper plus sulfate, so 4 oxygens plus a sulfur, plus 5 H2O. So it's a little bit more involved, a little bit more calculations to find the molar mass of the hydrate, but that's how you do it. We'll look at a practice problem in just a minute. Hydrates are kind of fun to work with. If you want to get rid of the water, you can basically heat up the compound, effectively evaporating the water away. And some hydrates will go through some really interesting color changes. So just by heating it up, you can change the molecule enough that you get a different color. And again, that's just happening from removing the water. So this is cobalt 2 chloride hexahydrate. And this is the anhydrous version of that, just cobalt 2 chloride with no water molecules attached. And even though it's just a physical change, we end up with a change in color. Let's try a calculation with percent hydration, and we'll finish up today's lesson. Okay, so we're asked in question 3 to calculate the percent hydration of each of the following. And let's take a look at NiI2,6H2O. So not that it's really part of this question, but the name of this compound would be nickel 2-iodide. We use the same prefixes for hydrates that we do with covalent compounds. You have 6, so that is a hexa. hydrate. That's it. Okay, so if we're trying to find the percent hydration, we know that we're going to have the mass of water. In this case, we've got 6 water molecules per NiI2 unit. I need to find the molar mass of nickel 2 iodide hexahydrate. Pause the video, calculate that mass. All right, I get about 420.5 grams per mole. If you round it to 420 or up to 421, to be perfectly honest, that doesn't really matter all that much. So I'll take that and I'll multiply it by 100 to find the percent hydration. So make sure you're entering things into your calculator carefully, and when you go through the calculation to the nearest whole number, I get about 26% water by mass. So if I was able to take a sample of that compound and heat it up, I could decrease the mass by roughly 26% as I drive off those water molecules. All right, I think that wraps it up for today. So if we just kind of look back at what we did, I know it was a big list of goals for the at the start of the lesson, but we can calculate formula mass now. We can calculate molar mass. Remember, it's the same mathematical calculation. We just have the change in units. You should now be able to calculate percent composition by mass. Mass of the element divided by molar mass of the compound times 100. And finally, percent hydration is just like a very specific percent composition by mass. It's looking at the percent of water present in our hydrate compounds. Nice job today, chemists. Thanks for tuning in, and I hope you found this helpful.